Hello everybody. Lecture week 12, session 3. Let's continue chapter 7. In chapter 7, we discussed entropy, the basic concept of entropy. Then you learn several methods to calculate the delta S for different cases. You learned that to calculate the delta S for reservoir. Normally, you can assume that they have constant temperature, so you can write delta S equals to the Q over T. Keep in your mind that the delta S can be zero, negative, or positive. However, the S generation, which is the combination of actually the total delta S, is always positive. So the delta S can be negative, positive, or equals to zero. For boiler and refrigerant 134A, we have tables of properties. So you can find S actually entropy per unit mass from the tables, and then you can find the delta S by just writing the delta S, S2 minus S1. This method, the second method, is just valid for water and refrigerant 134 because you just have tables, for these two substances. The third method that you learn, in previous lecture by using the Gibbs equation for incompressible substances, liquids and solids, you can actually write the delta S is C average, average specific heat at average temperature, ln T2 over T1. Keep in your mind that the temperature must be the absolute temperature. Then for ideal gases, you learn two different methods to calculate the delta S for ideal gases. If we assume that we have a constant specific heat or for small temperature ranges, normally less than 100 centigrade, the delta T less than 100 centigrade, you can use one of these two correlations to calculate the delta S or entropy changes. For the first one, use the first one when you have temperature and a specific volume or volume, and use the second one when you have the CP, temperatures and pressures. And then the last one that you learned last week, actually last lecture, was for ideal gases with variable specific heats. For a variable specific heat, you can actually use this method for air, nitrogen, oxygen, carbon dioxide, and these other substances. Why? Because in this method for variable specific heat, you need to actually have the S naught, and then we just have table of properties, in this textbook for these substances. So you can use this method to calculate the delta S for air and the other method. Keep in your mind, guys, in your textbook for air, you have the S naught, actually kilojoule per kilogram Kelvin. So you can simply calculate, use this method to calculate the delta S. However, for nitrogen, oxygen, and the other, ideal gases list here, you have the S bar actually not. The S bar not is entropy per actually kilomole Kelvin. So if you want to calculate the delta S for these gases, first you need to calculate the delta S per unit mole, and then you need to convert it to delta S per unit mass. How? By using this correlation. You can calculate the delta S bar, and then you can divide it by M. M is molar mass, and then you can calculate the delta S. So these are all methods, guys, a different method that you can use to calculate the delta S for all substances. Now you can calculate the delta S for all substances by using this four five different methods. So now let's just go into another example. Here you can also open the handout. Let's just open the handout, and then we can discuss in handout. Yeah. So but we have a piston cylinder device, and then it contains 5 kilogram of steam, and then we have the temperature, quality, and then this actually steam undergo two different processes. The first one, heat is transferred to the steam in a reversible manner, and then the temperature is held constant, and until the steam exists as a saturated vapor, and then the second one, the steam expand in a adiabatic reversible process, and then the final pressure is 15 kilopascal. So you in part A, you asked to just plot TS diagram. The second one, part B, you asked to calculate the Q for process 1 to 2 or Q1 to 2, and then the last one, part T, you are asked to determine W. So before you start to solve this, problem, I ask you guys to just complete this, table. So look, guys, you have some information for the initial conditions, and then uh, we have two different processes, and then the fluid is water or steam, and then this is a piston cylinder device. This is really important, guys. Why? Because if you need to write the energy balance equation, you should use energy balance equation for closed system, but not open system. So please pause this video, spend 2 minutes, and then just transfer all available information here into this table. Okay, guys. So I just complete, this table. You can see, the table here. We know that the mass is 5 kilogram. This is the closed system, so mass is constant. This is M1, M2, and M. And then quality is zero point 0.5. And then we have the temperature for, initial conditions. Now for process 1 to 2, this is a reversible process, and then we know that the temperature is constant. It's then we know that the um, actually second step is saturated vapor, the second state. So the X is 1, yeah. I don't know what is this 0. Okay, so X or quality is 1. For the third column, or for process 2 to 3, look, guys, we know that this process is adiabatic and reversible. So what is the definition for reversible process and adiabatic? If you remember from the previous, lecture, this is the definition for isentropic processes. So actually reversible process and adiabatic process are, isentropic processes. So process with these two, specification is isentropic one. Isentropic process, S1 equal, actually the entropy is constant, so we can write S2 equals to the S3. This is the actually main point, to solve this problem. So the entropy is constant, and then we have the P3, correct? This is P3 equals to 15 kilopascal. Now, to plot the TS diagram, let's go back to this. To plot the actually TS diagram, you need to have temperatures, and also you need to have, the pressures. So you have the P3. So what we need to do, we need to find P1 and also T3. Please spend 2 minutes and then find these two parameters, P1 and T3, and then you can plot the TS diagram. So 2 minutes, pause this video, and then find P1 and T3. Okay, look, guys, for the first step, we have the temperature. We know that quality is 0.5, so this is the saturated liquid vapor mixture. So the pressure equals to the saturated, pressure. So P1 is 101.42 kilopascal, and then for the third, actually state, so we have the pressure, and we know that this is the third state is actually saturated liquid vapor mixture. Why? I will show you why, this is a saturated liquid vapor mixture. So you can actually report temperature at this, pressure, the saturated, temperature at this pressure, which is 53.97. Now you have all actually required information. Please spend 2 minutes, pause this video, and then plot TS diagram. Okay, so look, guys, this is the general actual format of TS diagram. This is the DOM, and then for the initial state, we know that this is the mixture, and then quality is zero point 0.5. So temperature is at 100 degrees centigrade. This is the constant actually pressure line at 101.42 kilopascal. This line constant pressure line, and we know that we are in the middle of this line, correct? Because quality is zero point 0.5. Now for the first actually process at constant temperature, correct, and pressure, we move to state 2. We know that the state 2 has actually quality of 1, or this is a saturated vapor. So point 2 is exactly on the saturated vapor line. So we move at constant temperature and then reach to this point 2. And then from point 2 to 3, we know that this is an isentropic process. Isentropic process, are constant entropy processes. So we need to move actually to vertically. And then uh, we know that this final pressure is 15 kilopascal. So the final pressure is 15 kilopascal, and then we know that the final pressure, this is the T3. So the final temperature is 53.9. So this is lower than the T1. So we need to move downward, but not upward. Yeah, if the temperature was higher than 100, we need to move upward. So when you move downward, again will have the saturated liquid, saturated mixture. So the point 3 is on 15 kilopascal constant pressure line, and then we are here. So this is the TS diagram. Now for the next part, you asked to calculate the part B. You have to calculate the heat transfer for process 1 to 2, or Q1 to 2. So to calculate Q1 to 2, guys, you need to have an equation. You need to just write equation to calculate the Q1 to 2. So please spend 2 minutes and then write an equation to calculate Q1 2. 2 minutes, pause this video, and then write an equation to find Q1 2. Okay, look, guys, to write the actually equation to find Q, you need to write the energy balance for this, piston cylinder device. So this is a closed system. So for the closed system, you remember from chapter 4, you can write Q net minus W net equals to the delta U. If you assume that the kinetic energy and potential energy changes are negligible. Now let's simplify this equation. Q net is Q in minus Q out. Q out here is 0. We have the Q in. So this term will be Q in. What's about W net? W net is W out minus W in. Here, there is no W shaft, no electrical work. There we have only this boundary work. So this is the W boundary. When you add Q to the system, what happened? The actual piston moves upward, or we have expansion, correct? Meaning that we have W boundary out. So this W net is W boundary out minus W boundary in. So the W boundary in is 0, and then eventually you can write Q in minus W boundary, which is W boundary out here, equals to the delta U. So and then, if you remember, guys, again from chapter 4, the W boundary is P times V, volume, correct? So then if you bring the PV to the other side, the combination of internal energy and P nu will be the, entropy. And then you can write Q in equals to delta H, or M, H2 minus H1. So to calculate Q, you need to have M. M is known. M is 5 kilograms. You need to find H2 and H1. So you have two actually intensive property for both state 1 and state 2, so you can simply find H1 and H2. Please pause this video, spend 2 minutes, and then find enthalpies for state 1 and state 2, and then calculate Q in. Okay, so if you check the table, guys, and the first enthalpy H1 is, saturated liquid vapor. You have the quality. You need to use H1, HFG to calculate the H1. So also, I just list all, thermophysical properties here. I just report, the U2, S2, and then keep in your mind that the state2 is saturated vapor, so you need to report the Hg. From here, what you need to do, you need to just substitute the H2 and H1 into this equation to find the delta H. To calculate the Q in. So by using this method, guys, Q in is 5,641 kilojoule. So look, guys, this is the first method that I use to calculate Q. There is another method to calculate, Q. Please spend 2 minutes, pause this video, and then just try to find another method to calculate, Q. So pause this video and then just think if you can find any other method to calculate Q. So to actually find Q by using another method, guys, if you check, the actually state the question statement, problem statement, you can see that process 1 to 2 is a reversible one. So we already discussed that the area under the TS diagram for reversible process equals to Q, correct? Here, because we have S per unit mass, so the area will be Q per unit mass, correct? Or this lower case Q. So if you want to calculate Q for process 1 to 2, you need to calculate area under this curve or this area, correct? We need to calculate this area, and this is a really, simple. It's really simple to calculate this area. So to calculate this area, you need to have S1 and S2 and also temperature, and then you can simply calculate the area. So for the part, for the state 1, this is the saturated vapor liquid. You can use SFX, SFG, and then X is 0.5 to calculate the S1. S2 is, SG at, for the saturated vapor. So you have the S1, S2, and then you can simply calculate the area. Keep in your mind that the temperature must be in Kelvin, but not, centigrade. So from here, area under the curve is this actually the difference between, S2 and S1 times temperature. And then this is the Q per unit mass. If you multiply this value by M, which is 5 kilograms, you can actually find Q for process 1, 2. Look, guys, by using this method, the Q is 5,649, and the previous method, it was 5,641, just 8 kilojoule, difference. So you can use either the first method or the second method to calculate the Q. For the last part, guys, you asked to calculate W boundary for process 2 to process 2-3. So please pause this video, spend 2 minutes, and then write an equation to calculate this boundary work. Okay, so to calculate W23, you can again write the energy balance for piston cylinder. W net, Q net minus W net equals the delta U. So you saw that this is an isentropic process or adiabatic one. So the Q net is 0, correct? And then what's the W net? W net here is the W boundary. We just have, W boundary. There is no W shaft and electrical work. And then the W net is W boundary out minus W boundary in. Here we have expansion. So W boundary in is 0. So we can write negative W boundary equals the delta U, because this is W boundary out. And then we can just multiply both sides by the negative. This delta U is U3 minus U2. If we multiply both sides by negative, then we can write W boundary 2 to 3 equals to the M U2 minus U3. I just multiply this negative and then I just flip, the U2 and U3. So what you need to do to just find the W boundary 2 to 3, you need to find the internal energy U2 and U3, and you already found it, in the first part. So you have U2, U1. If you substitute here, you can calculate the W boundary. Okay, so isentropic processes of ideal gases. So you learn that the isentropic process are a process with actually adiabatic process with and reversible ones. So reversible and adiabatic process are isentropic processes. Here we can develop some useful equations for isentropic processes of ideal gases. So to develop these, correlations, if you remember, we already developed, three different, equations to calculate the delta S for ideal gases. So for the case one, if you remember, we assume that we have a constant specific heat. So, and then this is the first equation based on, the average, specific heat based on the average CV. So if we start from this correlation, and then for isentropic process, the left side is 0, correct? It's a, constant entropy. And then we can just simplify, this correlation. We can bring, the this term to the right side and then divide both sides by the CV. And then we can just, simplify this correlation into this format. Now, if you remember from, previous chapter, you learned that R for ideal gases equals to the Cp minus Cv for ideal gases. Also, we define K, a specific heat ratio, which is the ratio of Cp over Cv. Now, let's divide the both sides of this correlation by Cv. If we divide both sides of this correlation by the Cv, this will be R over Cv. This is the Cp over Cv, which is K, and then this will be 1. Correct? And then we can substitute for the R over Cv from this correlation into this one. If we just do this one and then we simplify this correlation, we will reach to this, correlation. So by using this correlation, guys, if you have the T1, let's say nu1 and nu2 for isentropic processes of ideal gases, you can simply calculate the T2. So by using the same actually, procedure and then using, the ideal gas equation of SD, we can develop two more, equations for isentropic processes of ideal gases. These are very useful correlation, guys, to just solve, to find the thermophysical properties of, isentropic process of ideal gases. So as a homework, guys, you can try to prove, the second and the third equations. Now, keep in your mind that, guys, these three correlations are valid for ideal gas, isentropic process, and constant specific heat. Or you can say these equations are valid for ideal gases, adiabatic process. We need to have a process that includes all these, criteria: ideal gas, adiabatic, reversible, and constant specific heats. Now, we can develop, guys, correlations for variable specific heats. For the variable specific heats, if you remember, guys, we just developed this correlation. On the left side, we have S2 minus S1, which is 0 for isentropic processes. Now we can bring S02 to the left side, and then we can just play a little bit, with this correlation, and then we can just rewrite it in this format. Then we can rewrite this the right side, into this format. This is the exponential of S02 over 1 over, S01 actually over R. Correct? We can write it in this format. Based on the definition, this term exponential S naught over R is called the relative pressure, PR, correct? PR. Keep in your mind that the PR is a dimensionless quality. It doesn't have the pressure, unit. Keep in your mind that this is a dimensionless, quantity, and then this parameter, relative pressure, depends on the temperature. Why? Because it's a constant value, and then if you remember from the previous lecture, S naught is a function of temperature. So keep in your mind that the exponential of S naught over R is relative pressure. Relative pressure is dimensionless quality, no unit. And then it just depends on the temperature, meaning that if you have the temperature, by using the tables, you can find this relative pressure. So based on this definition, you can write P2 over P1 for isentropic processes and ideal gases equals the PR2 over PR1. You can find PR from the reference tables. You have table, guys, for the PR, for the relative pressures. And those tables are based on the temperatures. So by using the same, actually, by using the ideal gas equation of S8, we can find a relationship for V2 over V1. So by using, the ideal gas equation of we can write the V2 over V1 equals the T2 over PR2 and over T1 over PR1. So the T over PR is called the relative specific volume, or VR, or nu R. So these actually values are available for air in table A17. And then keep in your mind that the nu2 over nu1, or V1 over V2, equals to the nu R2 over nu R1. So here, this is the table A17, guys. You can find the PR and nu R. If you have the temperature, guys, you can simply find the PR and nu R. Now, let's look at, the application of this, equations. For example, assume that you have an isentropic process, and then let's say, for example, this is a closed system. You have, for example, piston cylinder device, and then you have the P1 and T1. P1 and T1 and P2 are given. So these are all information that you have. You ask to find T2. Please pause this video, spend 2 minutes, and try to calculate T2 only by using the ideal gas equation of the state. Try to see if you can calculate, the T2 by using the ideal gas equation of a state. Okay, look, guys, it's impossible to calculate, the T2 by using the ideal gas equation of a state because the nu2 and T2 are, or V2 and T2 are an unknown. So it's impossible to calculate, the T2 by using the ideal gas equation of a state. However, by using these equations that you learned in this, chapter, you can calculate the T2. How? You have the T1. T1 is given. So by using the table A17, you can find PR1 for the air, if this is this process for the air. So you can find the PR1, correct? Now you have the PR1. You can use this correlation to find the PR2. Now you have the PR2. You can use table A17 to just read T2. So you can use the same, actually, a process if you have the nu to just find the T2. So here is the summary, guys. You just learned 5 important correlation. We will use this correlation in this chapter, in chapter 9, and also in intermediate thermofluid course, to design isentropic processes for ideal gases. So these are very important, guys, correlations. Next lecture I will solve some problems from this isentropic process of ideal gas, and then you can see the application of these correlations. uh, Please study the example 7.1 through 7.9 of your textbook. Thank you so much and have a great day.